So welcome back to Organic Chemistry, and in this video we're going to be looking at the organic families of alcohols and carboxylic acids, and we will be starting on page 28. So alcohols are our next family of organic compounds. They're our next homologous series, and do recap on your definition of a homologous series if you need to. So we know that with a homologous series, they're a family of organic compounds that contain the same functional group, show similar chemical properties, show a gradation in physical properties, and differ by a CH2 unit. And the same can be said for alcohols. You don't need to know alcohols in very much detail. You'll notice that it's just this page in your notes that are on alcohols. That's all you need to know. And in fact, we're about to draw an alcohol, but you don't even need to be able to draw the structure of alcohols. It's just so that you can actually see it. But the key thing to point out is that they are not hydrocarbons. So if you remember, alkanes and alkenes were hydrocarbons. So at the top of the page I've written their general formulas. For alkanes it was CnH2n plus 2, and with alkenes it was CnH2n. So why were they hydrocarbons? Well, they were hydrocarbons because they contained hydrogen and carbon only. Hydrogen and carbon only. So we'll see with alcohols that they also contain carbon and hydrogen, but they are not hydrocarbons because they contain oxygen as well as carbon and hydrogen. So let's look at the structure of ethanol, which is an example of an alcohol. You may have heard of ethanol before. As many different uses. It's used in the likes of hand sanitizer, but also alcoholic drinks. Ethanol is the particular alcohol that we use. Generally we use that term alcohol in general, but it's actually ethanol that all alcoholic drinks contain, and we'll see that in a second. So let's look at the structure of ethanol. So what can I tell from its name? Well, first of all, the start of the name tells me how many carbons there are in it. So F, how many carbons is that? That's 2. So let's draw 2 carbons in a chain. And then we've got anol. Anol tells us which family it's part of. It tells us it's part of the alcohol family. So that tells us that it's an alcohol. So F tells us there's 2 carbons. Anol tells us that it's an alcohol. So let's draw the alcohol structure of it now. So the alcohol group is O-H. So that's it drawn out in full with all the bonds. Carbon bonded to 1 oxygen, which is bonded to 1 hydrogen. If you think of the valency of oxygen, it's 2. That means it forms 2 bonds. So it is bonded to 1 of the carbons in the chain and then 1 hydrogen. And then all we have to do is fill up the rest of the bonds with hydrogens. So if we look at our first carbon here, it needs 1, 2, 3 more bonds to make 4, and we're going to put hydrogen at the end of each of those. And then this carbon, second carbon, it has 2 bonds already, so it needs 2 more, and we put hydrogens at the end of that. So in terms of writing the formula of this, how we would write this would be C2, the carbon chain. Around those carbons we have 5 hydrogens. You'll see I've drawn them in black and I've written them in black in the formula. And then at the end we have OH. So I know we're writing hydrogen again, but that tends to be the way we write the formula of alcohols, because it highlights that functional group at the end, OH, rather than just writing C2H6O. It shows really where the structure of that functional group. Again, you don't need to be able to write the formula of alcohols or draw the structure of them at this stage. But it's just helpful to look at an example of one to see that structure, and to see how they're different from alkanes and alkenes in that they're not a hydrocarbon because they contain carbon, hydrogen and oxygen. So that presence of oxygen means that it's not a hydrocarbon. So the only other thing you need to know in terms of alcohols is the preparation of ethanol from the fermentation of sugars. There are other ways of producing alcohol, but this is the only one that you need to be familiar with. So it may just be a simple 1-mark question of how can ethanol be produced, and you need to say by the fermentation of sugars. And you just need to know a few small practical details on what actually happens in this. Glucose is a type of sugar that's found in various fruits, like grapes, for example, that might be used to produce wine. And they can be fermented by enzymes in yeast. Okay, you've probably come across enzymes before in biology. Enzymes are biological catalysts. If you think catalyst is a word we've come across in chemistry as well. What does a catalyst do? It speeds up the rate of reaction without being used up. So enzymes are just biological catalysts. In other words, they are catalysts that exist in biology. They exist naturally in our bodies, for example. But here we're looking particularly at the enzymes in yeast. And that causes the fermentation of glucose. And that reacts to produce ethanol and carbon dioxide. And the equation is written there for you. Again, you don't need to be able to write a balanced simple equation for that or anything like that. So it's sugar, and in particular glucose. And it undergoes fermentation to produce ethanol and carbon dioxide. This is an example of what we call anaerobic respiration. Anaerobic respiration. So if you think of us respiring, we need to do respiration to survive. It's how we get energy from our food. So our equation for respiration is glucose plus oxygen gives carbon dioxide plus water. But what you'll notice here is that the glucose reacts without oxygen, and this is respiration for the yeast. This is a reaction you would have looked at way back in year 9 when you studied microbes and disease, and something you've probably covered in biology as well. So essentially the yeast is undergoing anaerobic respiration, that's respiration without oxygen, and as a result it's producing ethanol and carbon dioxide. So we use this ethanol and use it for the likes of hand sanitizing products and antiseptics in hospitals and things like that, but also for alcoholic drinks. So here you've got a few conditions, and you do need to be familiar with these. So the sugars, or the glucose in particular, is dissolved in a solution. So that's just essentially, they're not in a solid form, they're dissolved in a solution. You need to put yeast into the solution for the yeast to then respire, to essentially use up the glucose in respiration and produce ethanol. We need a warm temperature for this reaction to take place. We need it to be around 35 degrees C for optimum production, but we don't want it to be above 37 degrees C. Can you think why that might be? Why might we not want it to be above 37 degrees C? Well, that's because we're relying on the action of these enzymes in the yeast, and above 37 degrees, the enzymes in the yeast would be denatured. And that's something you've probably learnt about in biology, that enzymes work at a specific temperature and a specific pH. And any conditions too far outside these optimal temperatures or optimal pHs, the structure of the enzymes are actually destroyed, and they are denatured, in other words destroyed. The structure of them changes, and that means that they cannot do their job, essentially. And then lastly, our condition is we do it in the absence of air, because remember, this is anaerobic respiration without oxygen. Otherwise, what we would get would be glucose reacting with oxygen to produce carbon dioxide and water, just like happens in our bodies. So this we need in the absence of air. So we're producing ethanol rather than carbon dioxide and water. So after a few days in these conditions, essentially they're just left in, you can imagine, a reaction flask. The sugars in solution, the yeast in the solution, sitting at around 35 degrees C, covered so that there's no air getting in. So after a few days in these conditions, the yeast converts the sugar to ethanol and carbon dioxide. Once the concentration of alcohol reaches 15%, the yeast is killed, and at that point the fermentation is stopped, because if we don't have any yeast, we don't have this anaerobic respiration taking place, and ethanol will not be produced. So at this stage the ethanol is regarded as impure, because what you have got in your flask will be some ethanol, some unreacted glucose, but also some yeast. So we obviously don't want those in our ethanol, and so what we can then do is fractional distillation, which we've met in this topic as well, and we met last year as a method of separating a liquid from a solution, or one component from a solution essentially. So the ethanol is obtained by fractional distillation, and that gets us a more concentrated solution of ethanol, because you're separating the ethanol out from your solution that will contain glucose, yeast and ethanol. So that's all you need to know for alcohols. Essentially know that they're another homologous series. They're not hydrocarbons because they contain oxygen as well. And then just some brief details about how we produce ethanol from the fermentation of sugars. So next we're going to look at carboxylic acids, which is the final family of organic compounds that we need to look at. So again, they fit this definition of homologous series in that they're a family of organic compounds that contain the same functional group, show similar chemical properties, show a gradation of physical properties, and differ by a CH2 unit. And just as with alcohols, you don't need to be able to draw the structure of these, you don't need to be able to recall the formula or the general formula of these. But again, I'm going to show you one just to show again that they're not hydrocarbons, just like alcohols, and just to give you an idea of the structure of these molecules. So let's look at ethanoic acid, which is actually the acid that is present in vinegar. So the sour taste in vinegar, ethanoic acid is responsible for that. So again, what can we tell from its name? So eth, first of all, tells us that there is 2 carbons, and then the anoic acid tells us that it's a carboxylic acid. So that tells us it's a carboxylic acid. Okay, so let's try and draw the structure here. So first of all, we know that there's 2 carbons, so we'll draw those in the chain. Then what we've got is our functional group. Now our functional group actually contains that final carbon as well, and it's carbon double bonded to 1 oxygen atom. Remember, oxygen needs 2 bonds, so that's it, happy now. And then it's single bonded to 1 other oxygen, and then that oxygen is bonded to 1 hydrogen, a bit like what we saw with our alcohols. So that's the functional group drawn in, and all we need to do now is fill up our hydrogens. If we look at this carbon first of all, we can see that it already has 4 bonds. You can see 1 in purple there and 3 in green. So we don't need to add any hydrogens to it. But this carbon at the other end, it only has 1 bond, so we need to add 1, 2, 3 more and put hydrogens at the end of that. So just draw that in to show you. Again, you can see that it is not a hydrocarbon because it contains oxygen as well as carbon and hydrogen, so it doesn't fit that definition. A hydrocarbon is something that contains carbon and hydrogen only. So some uses of ethanoic acid which you need to be familiar with. It's used in vinegar. It's also used for other food flavourings and preservatives. So if you think of the likes of pickled onions, that is in a solution essentially of vinegar of ethanoic acid. So that's some uses of ethanoic acid that you need to be familiar with. And as we've seen with previous, for example, our alkenes, that the functional groups are responsible for the reactivity of that family of compounds. So with alkenes, the functional group is our C, double bond C, and that's where the reaction happens. That's what allowed addition polymerization. That's what allowed the reaction with bromine, for example. So with carboxylic acids, it's this functional group at the end that is responsible for the reactivity of carboxylic acid. And there's lots of reactions that carboxylic acids can do, but we're just going to be looking at one of them. And essentially it is one that we've seen before last year in our year 11 content, when we looked at the reactions of acids with metals, metal oxides, metal carbonates and ammonia. Because as the name suggests, carboxylic acids are weak weak acids. And so they show typical reactions of an acid, but they'll just react a little bit more slowly because they are weak acids as opposed to strong acids. So they'll react a little bit more slowly, but they show exactly the same type of reactions as the likes of hydrochloric acid, sulfuric acid, and so on. So we're going to recap those general reactions, make sure you would be able to write an equation for these types of reactions, and you would know the general observations as well if you were asked to recall those in an exam. So they react with metals, bases and metal carbonates to form salts, and also ammonia as well. So what we need to do is do a recap on naming salts. So say for example we were reacting magnesium and sulfuric acid. That's a metal reacting with an acid, so we would get salt plus a hydrogen, but we need to be able to name the salt. Remember, salts have two names. Where does the first name come from? It comes from the metal, and the name of the metal doesn't change, so I just write down magnesium. The second name of the salt comes from the acid, but that changes its name, so the salt is not magnesium sulfuric, the salt is magnesium sulfate. So the name of my salt when magnesium reacts with sulfuric acid is magnesium sulfate. So you can see the acid changes its name. So it says there, remember when naming salts, the second name comes from the acid, but remember that name changes. With carboxylic acids, they all change from their ending of anoic acid to anoate. From anoic acid to anoate. So what do we mean by that? So if we were using methanoic acid, the second name would be methanoate. So write that into the box there. So if methanoic acid was the acid we were using, the second name would be methanoate. If we were using ethanoic acid, the ending would change to ethanoate. And if we used propanoic acid, it would change to propanoate. So essentially your oic is changing to oate. So oic changing to oate, and you're dropping the acid. So these are all the second names of your salt. So say for example we were reacting sodium with methanoic acid, we would get sodium methanoate. If we were reacting lithium with ethanoic acid, we would get lithium ethanoate, and so on. You also will have to be able to write the formula of these salts as well, and that will involve swap and drop. And so you need to be familiar with the formula of these ions that are formed from our acid, and be able to do swap and drop with them. But the good news is all of this information is on the back of your periodic table. So what I'd like you to do is get your periodic table out and turn to the back of it. If you need a bit of time to get that out, pause the video and then start again once you've got it out. So this is what the back of your periodic table should look like. And actually, you may have never noticed before, but in the negative ions, you have all the carboxylic acid ions that are formed there for you, and the information is all there. So if we have a look here, and keep your notes open in front of you as well, the first ion we come across is methanoate. So think meth is one carbon. So methanoate is here, and its formula is HCOO minus. So let's have a think about that. If we were doing swap and drop with that, it would be HCOO, put that in brackets, and then a valency of 1. Okay, our next ion would come from ethanoic acid, because remember Eth is 2 carbons, so that's next in our series, and it forms the ethanoate ion, which is here. It's CH3COO minus. So again, if we were doing swap and drop, it would be CH3COO in brackets with a valency of 1, and you get that from the minus charge. Next in our series will be propanoic acid, which will form a propanoate ion, and again that's all there for you. The formula this time is C2H5COO-. And again, this shows you that we are following the definition for a homologous series because we're just adding on a CH2 unit each time. So if we look at methanoate going to ethanoate, and all we've done essentially is remove the hydrogen from the end, you can see here we've got CH and here we've got CH3 and then another C. So what we've added on there is 1 carbon and 2 hydrogens. So next in our series then will be butanoic acid, and that will form a butanoate ion, and that's up at the top here, butanoate, and its formula is C3H7COO-. And I know they're not in the order of how many carbons they are, but it's just because they're given to you in alphabetical order. So what I'd like you to do is to fill those formulas into your notes now. So pause the video and write those formulas into your notes for the methanoate ion, the ethanoate ion, the propanoate ion, and the butanoate ion. So remember, you need to be familiar with these formulae. You need to be able to use them, but you don't need to be able to memorise them because they will be on the back of your periodic table. Essentially what has happened with each of these ions is that it's lost an H+ ion from the carboxylic acid. And if you remember from last year, when a salt is formed, the hydrogen ions from the acid are replaced by a metal or ammonium ion. So in this case, with our carboxylic acids, it's that hydrogen at the end that is replaced. So if you remember from the previous page, this would be the structure of ethanoic acid. And you can see that I have highlighted in green there the hydrogen that will be replaced when this reacts with a metal or a metal carbonate or ammonia and forms a salt. So this is the hydrogen that is replaced. This is the hydrogen ion that pops off and a metal ion comes in. So when we lose that hydrogen ion, and remember hydrogen ion has a positive charge, so it loses the H+, when it's forming a salt, and that's replaced by a metal ion or an ammonium ion. So what are we then left with when it pops off? So this is what we're left with structure wise, but if we've lost an H+ ion, what do you think the charge is that we're left with on the main molecule? If we've lost H+, this is going to have a minus charge, and that's what attracts the H+ ion in the normal acid molecule. So our ethanoate ion has a negative charge, just as we've seen from the formula from the back of our periodic table, and this is then what we call the ethanoate ion. This is the ethanoate ion, and at this point that's where the metal ion or the ammonium ion will go. It will, both of those will be positive, so our metal ion will, say for example, be X+, our ammonium ion will be NH4+, and that will bond with that negatively charged oxygen. That's where it will go on in place of the hydrogen ion where that originally was. So you need to be able to write formulas of the salts that are produced from these reactions. So given a name of it, you need to be able to convert it into a formula. And all you need to do is simply do swap and drop with the metal or ammonium ion and the carboxylate ion. And what I mean by that is the likes of your methanoate, ethanoate, propanoate, so on. However, the interesting thing with this is that generally the formula of the carboxylate ion actually comes first. So you can see in the name here of our salts we would have calcium ethanoate, but actually by convention the ethanoate ion formula will come first, and then the metal or ammonium ion will come second, and we'll see that with our first example here. So I'm going to do the working out of this first example down below. It might be worthwhile getting a file paper or your blue book out to do the working out of this, because I'd like you to try some of these yourself, and there's not too much space in the boxes to get that, but make sure that you write the working out of this one quite clearly. So I've written the name down below here in 2 different colours. So just as with normal swap and drop, what we need to do is convert our names into formula. But just as we've said, the metal ion actually normally comes second when writing the formula of this. So instead of writing calcium, the formula of calcium underneath calcium, I'm going to actually write it underneath the ethanoate ion, and you'll see why in a second. So with calcium, our formula is Ca, and make sure you have your periodic table out. If not, please pause the video and get that out. If you look at calcium on the front of your periodic table, it's in group 2, so that means it has a valency of 2. And we'll write that in the top left hand corner. Then in terms of ethanoate, look at your table above, you've got your formulas there. It's written as CH3COO minus. So what do we need to do? Well, we need to write down the formula in brackets because this is a molecular ion. It has more than one atom within it. So if we're swapping down a number, which we will be in this case, we need it to apply to the whole molecule. So we put that in brackets, but notice we haven't written the charge. What do we use the charge for? We use that for the valency. So the charge is just minus or -1. So that means it has a valency of 1. And what you'll notice with all of these carboxylate ions, whether it's methanoate, ethanoate, propanoate or butanoate, they all have a charge of minus. So they'll all have a valency of 1. So that stays the same each time. So can I cancel this down at all? No, I can't. So I need to swap and drop. That 2 from the calcium is coming down to my ethanoate ion. So I write CH3COO. I need to keep the brackets in because the number is coming down for outside the brackets. So those brackets need to remain in. Then I write Ca. The 1 is swapping down from the ethanoate, but I don't need to include 1s in my formula. So by convention, actually the ethanoate will come first in this formula, which looks a little bit silly. But again, if you do it the other way around, it doesn't matter. The order of the formula doesn't matter as long as you've got the correct number of atoms, essentially. But conventionally, it's written this way, so we will do that in our notes. So your final formula is CH3COO in brackets, then your little 2, and then calcium. Let me do the next one with you, and then I'd like you to pause the video and try the rest yourself. So with sodium propanoate, again, remember we write the metal ion second. So sodium, look at the front of your periodic table, it's in group 1. So that's Na with a valency of 1. Propanoate, either look at the table above on page 30 or look at the back of your periodic table. Propanoate is C2H5COO minus, but remember we don't write the minus at this stage. We use that minus to get our valency of 1. You can see we've got both 1s here, so when we swap and drop those are going to disappear. That also means I can get rid of my brackets, so if there's no number swapping down, then I can get rid of my brackets. So it's just going to be C2H5COO Na. If you want to do that in 2 steps, so you could have written C2H5COO in your brackets, then Na. Then because there's no number here, then we can remove the bracket. So write that into your notes. So C2H5COO Na. So what I'd like you to do is to pause the video and get a spare page or in your blue books, try the working out of that and write your final formula in your notes, or if you want to just do it on a scrap piece of paper and then check the video to make sure you've done it right. But do pause the video, try and do these yourself so that you have a little bit of practice in it yourself. Just to say with ammonium, ammonium is on the back of your periodic table as well. Ammonium has the formula of NH4+. So it's also a molecular ion, it's a positive ion, so it will need to go in brackets as well. It will be NH4 in brackets with a valency of 1. So pause the video now, try these, and then check the video to see that you've got the right answers. Okay, so the next one was magnesium methanoate. So just to check you've got the right answer, methanoate is HCO minus with a valency of 1. Magnesium has a valency of 2, so that should have swapped down to our methanoate. and then you have your Mg. So your final formula should be HCOO brackets 2 and then Mg. Ammonium methanoate, hopefully you saw with those that methanoate and ammonium both have a valency of 1. So those cancel out, and so you'll have HCOO from your methanoate and then NH4 from your ammonium. Then lithium butanoate, well, the formula of butanoate will be C3H7COO, and then because lithium has a valency of 1 as well, there'll be no brackets with this one, and it'll just be Li at the end. And then finally with aluminium ethanoate, with the ethanoate part coming first, that's CH3COO. Aluminium has a valency of 3, so that will be swapping down to our ethanoate ion, and then just Al at the end. So those should be your final formulas. Just check that you've got them completely correct in your notes, because you don't want any mistakes in your notes. So the very last thing we need to do is look at some of these reactions that carboxylic acids will do. And this is absolutely nothing new for you, because we did the reactions of acids last year. We looked at the reaction of acids with metals, with metal oxides or metal hydroxides, with metal carbonates or hydrogen carbonates, and with ammonia. So nothing is new here. We're just applying it to carboxylic acids rather than the likes of sulfuric acid, hydrochloric acid, and so on. And as we said previously, these will react in the same way as normal acids, but just a little bit slower, because they are weak acids as opposed to hydrochloric acid, sulfuric acid, and nitric acid, which are strong acids. So they will show the same general equation, the same general observations. They'll just react a little bit slower. So let's first of all look at what happens when carboxylic acids react with metals. Well, we need our general equation here, which is metal plus acid gives us salt plus hydrogen. So in all of these reactions we'll produce a salt, but the side product will change depending on whether it's a metal or a metal carbonate or so on. So say for example we were to react magnesium with ethanoic acid, which I'm going to show you in just 1 second. We need to name our product, so we're going to get a salt plus hydrogen, but we need to name our salt. What will the name of our salt be? Well, the first name will come from the metal, which is magnesium, and the second name will come from the acid. Ethanoic acid is going to change to ethanoate, and you need to be able to write the formula for that salt, but you don't need to be able to write a balanced symbol equation for this reaction overall, which is good news. Plus then our side product, which is hydrogen, according to the general reaction or the general equation. So I'm going to show you this reaction now. Very randomly, I'm going to be doing it from my very own kitchen. So yes, I was in school yesterday, so I thought I would bring home some of these chemicals to show you these reactions, rather than just learning observations. But again, we saw these reactions last year. You'll have done these reactions yourself. It's just a metal reacting with acid, but in this case we have ethanoic acid. So in my conical flask, in my bottle here, I have ethanoic acid, which you can see just looks like any other acid, hydrochloric acid or sulfuric acid. It's a colourless solution. So let's see what happens when we add our strip of magnesium. So you can see it's not doing very much now, and as we said, these are weak acids, so they will react a wee bit slower than the likes of hydrochloric acid and sulfuric acid. But if you see here, you can see that we've got fizzing, so we've got a gas being produced. What is that gas? Well, it's hydrogen, of course, so we're seeing bubbles of a colourless gas, or fizzing you can just refer to. Okay. Eventually what will happen is that the magnesium will disappear. So when it's totally reacted, the magnesium will disappear. We may not see this on our time scale, because ethanoic acid is a weaker acid. If you think it's used in vinegar, so we don't want it to be too strong an acid, otherwise it would react very strongly with our teeth every time we put vinegar on our chips. So you see our fizzing, our magnesium will disappear. What we'll be left with then, you can see I'm not forming any colour of my solution, so I'll just be left with a colourless solution. And if you feel the outside of the conical flask, you can feel that it is warm. This reaction is releasing heat, just as any metal with an acid will do. So your 4 observations are fizzing or colourless gas produced. The metal will eventually disappear. We'll be left with a colourless solution and heat is released. So let's get those observations written into our notes. So we saw fizzing, bubbles of gas produced. We saw that the metal eventually disappears. We saw a colourless solution formed and heat is released. So get those written into your notes. And again, those are no different than the general observations we would have written down last year for a metal reacting with an acid. And then finally in our notes, we need to write in our gas test. What's the gas that we produced? It was hydrogen. So how do we test for hydrogen? That takes us back to our gas chemistry topic. And to test for hydrogen, we apply a lit splint. And if hydrogen is present, a popping sound will result. So make sure that is written into your notes before we then move on to the next type of reactions, which is with bases. So bases are compounds that will neutralise an acid, essentially, that will react with an acid to produce a salt and water only. And examples of bases would be metal oxides or metal hydroxides. So let's again think of our general equation for this. I advise learning the general equation and then you can just substitute in whatever particular metal oxide or hydroxide you have and whatever particular acid that you have. So a metal oxide or a metal hydroxide reacts with acids in the same way, and they produce a salt, as all of these reactions do, but this time instead of hydrogen being our side product, water is our side product. So write your general equation in there to help you learn that. So metal oxide or metal hydroxide reacts with acid to give a salt plus water. So let's say, for example, we had sodium hydroxide and methanoic acid. We know we're going to produce a salt plus water. So what's the name of our salt going to be? Well, the first name comes from the metal, and then we just forget about the hydroxide part. So the first name is going to be sodium. The second part comes from the acid, and methanoic acid will change to methanoate. And then our other product is going to be water. So not hydrogen this time, but water, because we've got a metal oxide or metal hydroxide here. We're asked for the reaction type here, and here we've got an acid reacting with a base to produce salt plus water only. This is something we met last year, but also this year when we were looking at exothermic and endothermic reactions. This reaction type is neutralization. We've got an acid reacting with a base to produce a salt and water only. I'm not going to demonstrate this reaction because it's not overly exciting. It's just mixing 2 colourless solutions together which remain colourless. But what we know of neutralisation reactions is that heat is released. It's an example of an exothermic reaction. But in terms of observations, you can't write down an observation that it's an exothermic reaction. Our observation, what we can actually see or measure, is that heat is released, the temperature will rise. And what we can deduce from that is that it's an exothermic reaction, but exothermic reaction is not the observation as such. And also the solution will just remain colourless. So the solution remains colourless. Both sodium hydroxide and methanoic acid are colourless. When we mix them together, they stay colourless, but heat will be released. Next up, we need to have a look at the reaction of metal carbonates with acid, with our carboxylic acid, and again this follows the same general equation as we would have learnt last year. So when a metal carbonate reacts with an acid, we're going to get salt, but what are our side products this time? This time we have 2. We produce water, as we did before, but we also form carbon dioxide. The clue with that one is we're reacting a metal carbonate and we form carbon dioxide. So let's say, for example, we had sodium carbonate and butanoic acid. So sodium carbonate and butanoic acid, what's our specific word equation going to be? So pause the video and try and write the end of that, try and name your salt, and then think about what are your side products going to be. So pause the video now and try and complete that equation. So what are the products of our reaction are going to be our salt, which, remember, first name from the metal, which is sodium. Second name from the acid, butanoic acid, is going to change to butanoate. Side products then are going to be water and carbon dioxide. And let's have a look at this reaction. Okay, so let's have a look at the reaction of sodium carbonate with, in this case I just have ethanoic acid again, but it would react in the same way as butanoic acid. I forgot to bring a spatula home, so I'm just using my teaspoon. But let's add the sodium carbonate to our ethanoic acid and see what happens. Okay, so what do we see happening? We see fizzing again, and that's because we're releasing a gas in this reaction. So we're producing a gas. What's our gas? It's carbon dioxide this time. So we can see that there is fizzing. And let's have a little closer look at our reaction. You can see the fizzing is still continuing. So you can see sodium carbonate before I added it in. It was a white solid. So it's now reacting with, in this case, it's ethanoic acid. To produce our salt solution, which will be sodium ethanoate, but sodium butanoate as we wrote it in our equation. It'll produce water, and it's also producing carbon dioxide, which you can see the bubbles of gas there. If I swirl it, you can see the reaction is still continuing. Okay. And what you can see is there's a little bit of sodium carbonate left there, but eventually when that all reacts, the white solid of the sodium carbonate will disappear. You can see a wee bit still there at the bottom, but eventually that will all react, or perhaps there's an excess of that, so I might need to add more of my acid. But eventually the white solid will disappear, and what will we be left with? Again, we'll be left with a colourless solution, so salts of sodium will form colourless solutions. There'll be white solids that form colourless solutions. So let's get those observations written in our notes. So first of all, we saw fizzing, or bubbles of gas released. We saw that the white solid disappears, so our white solid of sodium carbonate disappears. That left us with a colourless solution. And this reaction will also release heat, not quite as much as with the likes of magnesium metal reacting with the acid, but this reaction will also release heat. And then lastly, just to look at our gas test, well, in this case we're producing carbon dioxide as our gas, so we can't test it the same way as before as we did with hydrogen. And again, this brings us back to our gas chemistry topic. How do we test for carbon dioxide? Well, the test for carbon dioxide is bubbling it through lime water. And what will happen if we pass carbon dioxide gas through lime water? Well, the lime water will change from colourless to milky. Okay, so again with this reaction you need to know the general equation, so you could write a word equation for this reaction if you were asked to in an exam. You need to be able to specifically name the salt of a specific reaction. You don't need to be able to write a balance symbol equation, but you do need to be able to write the formula of the salt specifically. Your observations you need to learn, you see fizzing or bubbles of gas, the white solid of sodium carbonate, or say this was magnesium carbonate or whatever, eventually disappears. You're left with a colourless solution and heat is released. And if you were to capture that gas and bubble it through lime water, the lime water would change from colourless to milky, showing us that it is carbon dioxide. And then lastly, we've got our reaction with ammonia. And once again, we see that this is the same general equation for the reaction of an acid with ammonia. So you should be able to recall from last year that when ammonia reacts with an acid, we get an ammonium salt. So just like all our other equations, we form a salt. But in this case, we have no side products. It's just an ammonium salt. So say, for example, we had ammonia and propanoic acid. The name of our salt would simply be ammonia changes to ammonium. As we have seen, you use the ammonium ion from the back of your periodic table when getting the formula of this. And the second name of the salt would be from your acid, which is propanoate. Again, you need to be able to write the formula of that salt, but you don't need to be able to write the overall general balance symbol equation. Again, I'm not going to demonstrate this because it's not overly exciting. Again, we're just mixing two colourless solutions. And just as we saw with reaction type 2, we see that heat is released in this reaction. So heat is released and also the solution remains colourless. So ammonia is colourless and propanoic acid will be colourless. And then when you mix the two, they will stay colourless, but when they react together they will be forming a salt, ammonium propanoate, but the solution of that salt is also colourless, but heat will be released in the process. So it might be worthwhile going back to those 4 equations and writing the formula of your salt that you formed in each of them, just for a little bit of practice in writing salts. But other than that, that is this topic finished. So we've covered our 4 families of organic molecules. So we looked at alkanes and alkenes. We looked at their general formula, their functional group if they had one. For example, alkenes do have a functional group, alkanes do not. We looked at some of their structures, how we name alkanes and alkenes, and some of their reactions as well. With alcohols and carboxylic acids, we've just looked generally that they're not hydrocarbons because they contain oxygen as well. And particularly with carboxylic acids, we've looked at their reactions. And the very, very start of the topic, we also looked at fractional distillation of crude oil. So those would be the main sections of this topic. There is quite a lot to learn in it. There is a lot of reactions, a lot of different families here, and being able to learn the structure of particularly of your alkanes and alkenes and knowing the differences between those. So take some time now to review the whole topic, maybe make some revision notes, make sure you understand the differences between each of your families of your organic molecules. And check your specification to make sure you have covered and are confident in all points in this topic.